Okay, so we're going to talk about motion and velocity. So the T-shirt launcher project, we there's a lot of physics behind how to design it and how to make it hit the target. So the T-shirt launcher, one, the single most impactful thing that's going to affect where the T-shirt lands is gravity. And in our lab, we calculated, most of you guys were able to get close to negative 10. Some of you guys were spot on. The acceleration due to gravity is actually 9.8 meters per second squared. And the negative just means that you're going down, that you're falling down. Okay, that's what that means. So a lot of you guys got numbers around there. Some of you got 9, some of you got 10, some got 11, some got 8. But if you average the averages, that was pretty good. So the frame of reference of a system of objects that are not moving compared to an object that we are watching. So frame of reference is, look at yourselves right now. You're sitting in your chairs, and you could even say you're not moving, right? But the Earth is rotating on its axis right now. So from this classroom's perspective or frame of reference, you guys are sitting in your chairs not moving at all. You are going 0 meters per second. But if you were on the moon and you watched us, we'd be flying. We'd be like, going really fast. And so how fast we're going is relative to our frame of reference. So a telephone pole is a good frame of reference when you're judging the speed of a car, right? So if you're in your car, and this is another great example, if you're in your car with your family and you're going somewhere, whoever's sitting in the car with you, they're not moving with regards to in the car, right? If they're sitting in the seat next to you, they're not moving any faster or any slower than you, so they appear to be standing still. But if you look out the window and you see a telephone pole and it goes, that's how fast. You guys should practice that noise. No? Okay. So, too early. But that's really how fast you're going in that car. Now, if we were watching the car from the moon, that car would be going really fast, and it could be going with the direction of Earth rotating. And by the way, Earth is also orbiting the sun. And the sun has its own path. And the galaxy is in a spiral, and the universe is expanding. So depending on your frame of reference, you're either going really, really fast or not so fast. So a telephone pole is a good frame of reference because when you're in the car and you look out the window, because the telephone pole is stationary and you go flying by it, you go, wow, I'm really going fast. So the next time you guys are on the highway, try to look at a sign and see how fast you go by the sign. And then look to somebody next to you and then think about how fast they're going. So some examples of this is a cloud in a plane or a car in a tree. And I have a little YouTube video I'm going to play for you guys. It's pretty cool. And this has to do with frame of reference. So you just got to think about the frame of reference of this airplane. Oops. It's a short video. If I can get my... So when you look at that, how fast was that airplane going? It seemed like it just floated and landed, which it kind of did. What did you notice about the propeller? Sometimes it looked like it was going, sometimes it looked like it wasn't. Okay? Does everybody have this written down? So if you look at this car, you could see that the second car is in motion, can't you? Based on a frame of reference. In the first picture, you see that the tree is kind of standing still. In the second picture, you can barely make out what's going on. It's the same photo, though. One, the person is standing still. The first photo, somebody's standing still. On the second photo, they're driving past. So the silver car is sitting still. In fact, notice that this is the same white building, and this is the same tree. So this person is taking a photo straight on, and this person is whizzing by as they take the photo. So here's a possible test question that you'll need to write down in your notes. Probable is a better word. Two trains move in the same direction and speed. You look out the right window and you see the other train. You look out the left window and you see trains moving by. Looking out which window gives the best frame of reference for you to judge the speed. Well, what do you think? Which one gives you the best reference? If I look out the window to my right and I look like this, and there's somebody sitting in that train and we're both going the same speed, and I look at that person, they're not moving forward from my frame of reference, they're not falling behind me, we appear to be going about the same speed. Now, I can probably in the background with my eyes and my peripheral see that there's some sort of motion in the background. But if I just look at that person, because that person isn't moving any faster than I am, it looks like we're both sitting still. Because we're not moving with regards to one another. But if I look out the window to my left, I see things flying by. So if I'm trying to gauge the speed of the train, it's probably better that I look to my left. All right, does everybody have this written down? So going to the left is what we want to do. So relative motion then is movement in relation to a frame of reference. Einstein did a little thing on this, theory of relativity. Of course, that deals with special relativity, deals with stuff that's going really, really fast, like the speed of light fast. So if I were to calculate how fast I'm going in regards or with respect to you guys sitting in your chairs, I'm not moving at all. But if I calculate how fast I'm moving from a perspective of the moon, and I can see where I'm at, measure where I'm at, and then a couple seconds later, the Earth rotates pretty darn fast. So depending on my frame of reference, it looks way different. Right now, I look like I'm going 0 miles per hour. But if I were on the moon, it would look like I was going 1,000 miles per hour. That's how fast the Earth rotates. And that's at the equator. We're not at the equator, so I'm not traveling as fast. But at 1,600 kilometers, it's actually 1,609 kilometers per hour. That's quite a bit. Oh, no, it's just 1,600 kilometers. Well, no. Yeah, it'd be 1,609. That's pretty fast. So when we go to figure out motion and velocity, and we did a little bit of this when we did our t-shirt drop, Mr. Adams is going to talk about distance and displacement. But distance is how much ground you covered, how far you went, right? That's not grammatically correct. How far you went, how far you go. I don't know. When we measure stuff. So if you measure from the moon, and I'd have to do the math, but if I sat in this chair for an hour and didn't get out of this chair, and you were to measure how far I've moved in this room, it would be zero meters per second. But if you measure that from the moon, it would say I'd be at one point. You're looking from the moon, and then Mr. Adams will be way over here. I'd be in 1 hour. That means I've moved 1,000 miles. Well, if I was on the equator, we're not on the equator, so it's probably not. It's probably a smaller number. But the two are different, right? And it's all based on the frame of reference. Well, distance is kind of like how many steps you take. So if I get up and I walk over to the door, or if I walk all the way down to the cafeteria, and then I walk all the way back from the cafeteria and come back and sit down in my chair, the distance that I traveled would be like thinking about how many steps I took to get to the cafeteria and how many steps I took to come back, right? And it kind of looks like this. Where I start and where I finish. Okay? It's how much distance I covered. Now, I really want to have you guys understand that there's a subtle difference between this and displacement. Does everybody have this written down? So you're really worried about, well, let's just move on to the next slide. Now, displacement is how far an object is placed in a straight line from start to finish. You could think of it as a shortcut. For physics, everything that we measure with regards to distance or displacement, it has to be in meters. Okay? Has to be in meters. Displacement is also a vector. And we'll unpack that quite a bit, but I just should probably mention it right now. A vector has a magnitude, a measurement, a number, and a direction. And how do we represent the direction? Well, we would say it's positive or negative, right? We would say that it's positive or negative. So distance is just the number of steps, and displacement is the shortest path from beginning to end. So let's unpack that same scenario. Mr. Adams gets up out of my desk, walks out in the hallway, walks all the way down to the cafeteria, turns around and comes back and sits in my chair. Where did I start? Here. Where did I finish? Here. The distance is how many steps I took. Or you can measure it in feet if that makes it better. How many feet? Well, I walked, about 10 feet to get to this space, and then I walked down the hallway 40 feet, and then I walked down the other hallway 40 feet, and then I walked across the front commons 30, 40 feet. Then I turned around and did everything backwards. 30 feet back, 40 feet back, 40 feet plus 10. And you add all that up, that's my distance. Now displacement is, where did I start? Here. Where did I end up? Here. How much did I move? I moved a lot, but my displacement would be 0 because it's the shortest distance from the point that I started to where I finished. Now, usually it's a straight line if you think of it in terms of vectors, which you don't. I'll teach you about vectors. Okay? Can I move on? So what is the displacement when you walk your dog? Well, if you think about that, you take your dog out of your house, probably by the front door or back door, depending on how your house is. I would do it out of my side door. I don't have a dog. If I did, I'd take it out the side door, but then I'd walk it around the block, and I'd go right back in the side door. So what would be my displacement? 0. It would be 0. I was not displaced at all. Okay? Now my distance would have been, if you were to measure the total distance that I went to walk around the block. Okay? Here's a great example. I got to zoom out a little bit on this one. You guys recognize that? So this is that classroom over there. And this is the door. Well, it's not really a classroom, but this door you walk out over here, like when we have a fire drill, this is that door. This is the high school in green and gray. And let's say you want to walk to, what's the name of that gas station? Family Express, right? So at the end of the school day, you want to compare and contrast the distance versus the displacement. So you walk out this side door, which you're not supposed to do, but you're a rebel and you break the rules. And you walk out this door and you walk out to the road. Well, the yellow path is the path that you would take, right? Because you can't walk through the building. So you would take that path to the sidewalk, right? There's a sidewalk that leaves the building and goes out here. And then you go down all the way to the parking lot of that gas station. And then you have to walk into the front door. The distance would be that total distance. So I'd measure whatever this is, and measure whatever this is, and measure whatever this is. And that's the total distance that you would travel. But displacement is just going, okay, from here to here, what's that distance? Right? It's really a measurement. What's my displacement? So the displacement's in red, but the distance is in yellow. Does that make sense? Now, in physics, we tend to work with vectors more. We prefer the displacement because it helps us to determine the position of something, like where the t-shirt will land. So we want to know about where the t-shirt will land. We don't need to know if the wind blew it up a little higher than it was supposed to. We just want to know where it will land. Does that make sense? We don't necessarily care, and I'm not saying this is what a t-shirt would do, but I don't care from a physics perspective if the t-shirt goes this way, and this way. I just want to make sure it lands here. So we do all the physics and math using vectors. Okay. Can I move on to the next slide? So here's like a different angle of that. Now vectors, so we use vectors to track that stuff. So you need to write this down. Vectors are basically, they represent the magnitude, and the actual vector itself is the magnitude. So the longer the arrow of the vector, so it's a visual representation of something. Motion, displacement, acceleration, force. So a long arrow represents how big it is. So this vector might represent a displacement. But the vector also has a direction. So if it points in a positive direction, and we can choose what's going to be positive and what's going to be negative, and you have another vector that points in the opposite direction, that would be negative of the positive, right? Think of a number line. If I go this way, isn't that all the positive numbers? If I'm 0 and I go this way, isn't that all the negative numbers? So think of a car. I can go 20 miles per hour this way, or I could go 20 miles per hour this way. Well, what vectors do is they say negative 20 miles per hour, positive 20 miles per hour. And the positive and negative sign tells you which way to go. Does that make sense? Now, the arrow represents the magnitude. So this arrow is probably about 10 times bigger than this arrow. So this is 10 times faster, 10 times longer, 10 times more powerful than this one. Okay? Did you guys draw the arrows? You got to draw the arrows. Write down that the longer arrow is more whatever it represents. So sometimes we say the force. Sometimes it can represent power. Sometimes it can represent velocity or speed. And the smaller arrow is slower or weaker. Okay. And we'll do a whole thing on vectors. All right, let's move on to the next slide. So one of the things that we could do for vectors is that we add or combine one or more velocity into a result. So these two guys right here, this guy is pushing it, the green guy is pushing it with a certain amount of force in this direction. Okay, let me zoom back in on that. So this green guy is pushing in this direction, and the blue guy is pushing in this direction. Which way will the box go? Well, it's going to be a sum of these two. So it kind of goes in the middle, right? But we can mathematically determine that, exactly where it goes and exactly how fast it goes. What you do for vectors, and I'm going to have to zoom out again. For vectors, what you do is you do this thing that we call the tip-to-tail method. Which you can't really see because it's not in the drawing. Yeah. Huh. But somewhere over here, let me move this over a little bit. So what you do is you can find the resultant vector by putting the vectors together, and the magnitude of force, this is going to travel from here in a straight line to here. That's how you calculate that. That's how we're going to predict where the t-shirt lands. Okay? So by combining one or more velocities or forces or whatever it is that we're measuring in a physics class, we could determine the direction of the path. So in our t-shirt launcher, we're going to figure out the up and down velocity and the left and right velocity, and that'll determine where the t-shirt goes. Okay? Does everybody have that written down? You don't need to draw the car. I don't know why they have the car there. So now here we have two vectors. So I have this vector, and it's usually tip to tail. And I have this vector. So when you add them up, they should equal the same thing. Okay? But that's not tip to tail, this is tip to tail. This isn't drawn accurately either. So if this is a positive 3, then this would be a negative 4. So my resultant vector would be the difference between these. So this would be negative 4 plus 3. What is this value going to be then? Well, this would be negative 1. Okay? And I'll go over this again. I'm hesitant to write on this because every time I write with my tablet on this software, the whole thing crashes. So let me do another example. If I have two monster trucks pulling this car, you would take this vector, add it to this vector, and that's the route that the car will take. The car will just keep going from here to here, even though the two trucks are pulling them in different directions. So this is a better example. If I have a positive 10 vector and a minus 9 vector, what am I left with? You're left with positive 1, right? This is actually what's left over. And so you know that 10 minus 9 is 1, but if you were to do that on the number line, it would look more like this. Well, we'll just leave that like that. That's not written right. Just ignore that. If I have a boat going this way, the boat's path is going to go from here on an angle to here. Does that make sense? And they're saying the wind is blowing, right? This is the wind blowing. So it's going to blow it at an angle like this. And that's it for today.